Okay, so if we have a graph which is a regular lattice, so something like this. So this is a line graph, would be sort of a one-dimensional lattice. But you can have a two-dimensional lattice. You could also have a three-dimensional lattice. The only important thing is that you have a graph where all of the points are sort of regularly spaced. And for now, we assume that they are densely connected. Any graph that is adjacent, any vertex that's adjacent to another vertex in like sort of this implicit coordinate system, I mean now it's explicit because I wrote it down like this, is like connected densely, so like it's all tiling. If we have a graph like this, we can represent it just with a coordinate system. You can say this vertex is at, for example, 0, 0. This vertex is at 1, 0. This vertex is at 2, 0. And here would be 0, 1. So that's like discrete sort of Euclidean plane, I guess. It's isomorphic to that. That means if we have a graph that is like this, we can represent it just in terms of the coordinates that we have. And then what we can do is, for example, imagine we want to figure out how can we go from this node here to this node here. What are like possible paths to there? And we could do like, usually we would do in a graph, we can just do depth first search. So we would be like, I can go like here, and I can go here, I can go here, I can go here, I can go here, and I traverse like the entire graph by unrolling it in this way. And at some point I will end up at this vertex. That is like the one that I want to get to. So we need to do this entire unrolling procedure. So imagine the graph is very large. We have like 1 million times 1 million is the number of vertices. So like we have a quadrillion number of vertices. So now this tree search would take a lot of time. But if we have just this regular coordinate grid, it's actually the same. Or like what we can do is we would say something like 1, 2, 3. So this is at 3, 3. And then we can ask, how do I get from this to this? Well, we can just say these are sort of vectors. And we subtract these vectors such that we sort of just calculate this vector here. Like this is the vector we get, which is 3, 3. But it would work with any arbitrary 2 points. So now we reduce this like problem of how do I find sort of how to get here from doing all of this search in the tree to just subtracting 2 integers, basically. And that's a lot more efficient. Now, one problem is that this doesn't correspond directly to we have this vector, but really this is not like a path that we have. But we can easily convert it to the path. In fact, we can do the thing where it's like this vector gives us all possible paths that we can use to reach here. Also, we're now assuming that this is just an undirected graph, meaning we can like move anywhere. If we assume that, what we can do is we can interpret this as saying any path that goes 3 to the right and 3 downward gets me to the target. So this would, for example, be this.
It's actually
path.
3, 2.
3, 2.
Or 2, 3 actually. No. 3, 2. 3, 2, correct.
Oh yes, it's actually 3, 2. And now we have, like, for example, this path, the blue path. But you could also like take like this path. It also works. You could also take the path where we sort of like go here, go down, go back, go down, go here, go down, go here. Because if we sort of like sum all of the movements on the x-axis or on the y-axis, is also 3, 2. So like, in some sense, this tells us all the possible paths that we can take in the lattice. I also assume that we don't have weighted edges because these different, like for example, this path that goes in a zigzag would have like more cost associated with it if we like have, but if we just have more edges in it.
Yeah, I mean,
but if we
it
don't
always
care
has
about the
more.
weights, then this, we can use this in an arbitrary large lattice graph. It could be 3-dimensional, and we can just analytically compute sort of like all possible plans. Or I mean, it would be easy to limit it such that we don't get the zigzag. Then we just say only the paths that increase. But that's what we can do, right? We can analytically calculate the path between two vertices, or even like sort of a piece of data that describes all of the paths, from which we can sort of like, that's like, we can interpret this as this mathematical condition that is filtering all paths.
Yeah.
Or that we can use even to construct all paths. I mean, that's the important thing, right? Like,
you can write down like an O of 1 algorithm, which gives you a path. It just does the subtraction, and then
it actually doesn't give you a path.
No,
but it does give you the object from which now it's easy to like generate a path. And also like you could do it lazily.
I could down an algorithm that generates the path from this, which is
though that like would not be O of 1. This would be dependent upon the path size, I guess.
What? No. What? I can just say go 2 down and 3 to the right, and then I'm done.
I mean, depends how you, yes, you can, if you represent the graph like this, the path like this, then yes, that makes sense.
I mean, it doesn't work if there are obstacles.
Yes, there might be some obstacles such that, for example, if this is not traversable, like this node doesn't even exist, let's say. So they also don't have these edges. Now you cannot choose an arbitrary path from here to here. And we would need to do something else. But the basic idea is that if we just have a completely regular lattice, then this works.
Yes.